So, in this lecture, we will talk about valuation rings and discrete valuation rings. And these concepts in commutative algebra very useful in when you study abstract algebraic curve or in terms of valuation rings of the function field, or when you think of divisors and line bundles, you will see that this is valuation ring has a very great impact on this for further studies. Okay, so let's start with a field. And the nice thing is that you can start with any field. You don't need to be any algebraically closed field or anything. So it is very general. So let K be any field. So a subring. So this is the definition of what is a valuation ring. So a subring R of K is a valuation ring, or sometimes I call valuation ring of K if for any alpha non-zero in K, either alpha belongs to R or alpha inverse belongs to R. Okay, so now there are two things. First of all, why such a ring exists, and even if it exists, then why it is it unique? So there are two questions. Why such thing exists? Another thing, if exists, is it unique? So why such thing exists? Of course, when you define something, it exists. So you can prove this. I will show it. We'll see that using Zon's lemma, one can prove that such thing exists. And if it exists, of course, it is not. It is not unique. So a field can have different value. I mean, many valuation ring. Okay. So just before that, let's see some examples. So our favorite example, K you take to be the rationals, K equal to Q, and take P to be any prime, number. Then you consider the localization of Z at P. So that is, which is nothing but, so this is the ring. So this is nothing but P to the power R M by N, where R is greater than equal to 0 and P does not divide M, P does not divide N. Right. So it is easy to check that this is basically the localization of the integer ring at the prime ideal P. So this is a valuation ring. Easy to check that. So exactly same way you can do it. Instead of K equal to Q, you can take K equal to be say Kx. K is any field, and take R to be sorry, not Kx. K, this is not a field. K to be take Kx, where x is a variable. So take R to be Fx by Gx. Of course, Gx not equal to 0. So the degree of F is less than equal to degree of G. You can check that this has this property. If I take any element, so any element F by, it is of the form F by G. Now there are two possibilities, either degree of F is greater than equal to G or degree of F less than equal to G. If degree of F less than equal to G, then it is in R. If it is greater than, then you just invert the element. Since it is a non-zero element, fx will be non-zero. So the okay. So g not equal to 0. Okay. Now, before we prove the existence, we need a theorem, or this is like a extension theorem. In field theory, you have seen. So same thing holds for rings. So let R be a subring and H is a ring homomorphism R to omega, where omega is an algebraically closed field. Okay. And this is a ring homomorphism. Now, now suppose let alpha be a non-zero element. Then this H can be extended to the polynomial ring R alpha. So then H can be extended to a ring homomorphism H bar from R alpha to omega. So R is sitting here and you have already have a H map. So this H map you can extend it to this R alpha to omega. So the proof is not very difficult. It is just when you take R to be field, it's like you attach a root. So in the case of rings also exactly follows the same rings. So idea is I will not give a full proof, but idea is to so you consider what you do, you take the polynomial ring R of x and then you take the ideal I where if all those fx such that f of alpha equal to 0. Now you take the image of this ideal, okay, image of this ideal. Now so of course, yeah, sorry, Rx to omega x. This is just a, if you take any polynomial here, summation ai x power I, you send it to summation ai h of ai time x to the power I. So this is linearly you extend, and now what you do, you take the ideal I, which where the all those functions in Rx, but f of alpha is 0. Okay. Now when you take the image is an ideal. This is a principal ideal, so it will be generated by a single element. So take the root of that so you consider h of I, h bar of I. So h bar I will be some generated by some polynomial g, and consider g to be, so g will have some, so this is a polynomial, so omega is algebraically closed field, so it will have some root beta. So you call that beta to be, so you send alpha to beta, and that is the actually required morphism from R alpha to omega. So that's how, I mean, this is a very rough idea, and you have to prove many things here, that it does not depend on the this is well defined map h bar this way, and so just like in the field, in the case of fields, you do you extend. This is the extension theorem, field extension theorem. This is, I can call this as a extension theorem for rings. So it's exactly same idea, but this case it will be little careful for rings. Okay. So I just leave these details as exercise. Details you check. So I leave it as exercise. This follow the in the case of fields. Okay. So now we will use this theorem to prove our existence of valuation ring. So that is important here in our case. So this is its existence of valuation. So let R K be a subring and H R to omega, where omega is a field and omega is algebraically closed. Then H has a maximal extension V comma H bar. That is, I have a R. This V is a subring of K, which contains R, and V to omega you have a map which is H bar, which commutes with which when you restrict to R is H. And it is maximal in the sense means that this is the largest subring of K containing R such that H bar restricted to this means that H bar restricts to H is equal to H. Okay. Further, so this is first of all there is a such maximal extension. Further, any such maximal extension, there need not be any unique. Further, any such maximal extension, any such V comma H bar or any such V is a valuation ring. Is a valuation ring. Okay. So this is how you prove existence. So as you see, as you know that most existence proof in commutative algebra, you take help from Zorn's lemma. So here also we will do the same. So let S to be the set of all such Vi, Hi, such that R inside Vi inside K, and this is Hi to omega, and R to omega you have a map. So Hi, so this means that Hi restrict to R is nothing but H. Now you see that now you use you consider a chain of such thing. So you define your ordering that Vi comma Hi, or let's call it Ri. Okay. Because generally VI denote V stands for valuation ring. So any such, so you define Ri comma Hi is less than equal to Rj comma Hj if you have Ri is a subring of Rj, which is a subring of K, and you have this Hi which is omega, and this is Hj, sorry, omega, this is Hj. If this Hj, that means Hj restricts to Ri is Ihi. Okay. Now, if you consider a chain, then it has a maximum element. You just take the union, and then it has a maximum solution by Zorn's lemma. So, you apply Zorn's lemma. There exists a maximal element. So, call it V comma H. Okay. So, now what I want to show that this VA, so let us call it V comma H bar. So, I claim is that this V is a valuation ring. Of course, it is a subring of K, is a valuation ring. But that is obvious, because if I take any element alpha in K, then you consider the V of alpha. Now, by use the previous theorem, alpha is a K. So, K now V alpha to omega, you can always V to omega, you have a map H bar. So, by the previous theorem, if alpha is in V, then it is fine. If alpha is not in V, so you consider V alpha. So, now you can extend it by previous extension theorem, because omega is algebraically closed. But V is contained in V alpha, and when the extension, so if I call this H tilde, H by definition H tilde restrict to V is nothing but H bar, right. So, now by maximality V equal to V alpha, but V equal to V alpha will say V equal to V alpha or V equal to V alpha inverse. Right. So, this will say that alpha belongs to V or alpha. Okay, by maximality. Okay. So, this is what is so now you know that if you have a field K and you start with see, generally what you do, you start with the domain, integral domain, and you take the quotient field of R, and this is your K. Now, you find valuation ring of K which contains R. So, this is how the things go, I mean, in practice. So, now so some properties of valuation ring. First is the function field of K. First of all, V is a domain, because V is a subring of K. So, quotient field of V, sorry, not function field, the quotient field of V is equal to K. So, this is very easy, because because of this property that alpha belongs to, because alpha belongs to V or alpha inverse belongs to V. For any alpha belongs to K minus 0, say. Second property, so any subring, again this is because of the same property, any subring V prime containing V suppose V is a valuation ring, containing V is a valuation ring. 3. This is very important, that V is a local ring. So, this requires little proof. So, let us look at it. So, consider MV, these are non. So, how do you prove local ring? Local ring means you construct, there is a unique maximal ideal, and outside that maximal ideal everything is a unit, right, because it has only one maximal ideal. So, you consider all the non-units of V. So, if I prove this is a ideal, so and it has to be maximal ideal because you are considering all the non-unit. So, that will show that V is a local ring. So, how do you prove that? So, you take, so to prove something is ideal, you take two elements A and B not equal to 0. Consider A by B. So, now A by B is an element in the quotient field, right, of V. So, now A by B either, so by definition A by B belongs, because V is a valuation ring, either A by B belongs to V or A by or B by A belongs to V. Right. So, now you write A plus B as B times 1 plus A by B. So, now A B belongs to MV. So, this will imply this belongs to MV, because if it is not, so if it is not in MV, that means if it is a unit, that means B that, so if not, B 1 plus A by B is unit, but this will imply that B is unit, which is a contradiction because we have started with something non-unit. Similarly, if B by, so this is when A by B belongs to V. Now, similarly, when you take B by A belongs to V, exactly same way you can prove that this is this will say that A plus B belongs to MV. Exactly same way you can prove that this belongs to. So, if you take two elements in MV, their summation. Now, if you take now what you have to prove, that if I take any element R in V, then R time A belongs to MV. But that is obvious, because if it is not, then if it is unit, then that will say that A again is a unit, right. So, this is obvious. So, this shows that, that V is a local ring, and the maximal ideals is given by the non-units element of V. So, okay. So, this is a very important property, that valuation rings are local rings. Another important property is that valuation rings are integrally closed. We have already seen what is called integrally closed. So, that means V is integrally closed. So, that means V contains K is a quotient field of V, and any element of K which is integral over V, it has to be in V, right. So, suppose, proof is obvious, like suppose alpha belongs to K is integral over V, then alpha power n plus say C n minus 1 alpha, say alpha not equal to 0, C n minus 1 alpha power n minus 1 dot plus C not equal to 0. Then alpha power n, you can write it as minus of C n minus 1 alpha n minus 1 plus C naught. So, claim is that this either claim is this alpha belongs to V, right. So, claim if it is something is integral, so claim is alpha belongs to V. So, suppose alpha not belongs to V. So, claim alpha belongs to V. So, suppose not, then alpha inverse should be in V, right, because by the definition of valuation ring, where V is a valuation ring of K. So, alpha inverse belongs to V implies that alpha power 1 minus n, which is nothing but alpha inverse of n minus 1. So, this belongs to V. So, if you multiply star by alpha, multiply star by alpha 1 minus n, multiply star by alpha 1 minus n. So, then what you get? You get here alpha minus C n minus 1 dot 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 C naught alpha inverse of n minus 1. Right. Now, by definition, the right hand side belongs to V, because alpha inverse. So, everything is power of alpha inverse. So, right hand side is a power, it is in V. So, that will say that alpha belongs to V. So, hence V is integrally closed. Okay. So, this is a property. Another important property it has, that these ideals of valuation ring, they are ordered, in the sense that if I take two ideals I and j in V, then either I is a sub of j or j is a sub of I. So, that is the ideals of V are totally ordered. So, this is so, these are some important properties. And another important property is that localization and the quotients of valuation rings are on prime ideals are valuation rings. So, if you take a prime ideal P in V, it's a prime ideal, then you consider Vp the localization, and localization at the prime ideal Vp, and the V mod P these are valuation rings. So, these are some standard properties of valuation rings. So, you can check this as these two as exercise. And another important thing is that that integral, suppose, so you see, remember that you started with the valuation, you are taking a subring of the field. So, now the integral closures of R in K. So, this is integral closure of R in K. Then R bar you can write it as R of V, or this is a V is a valuation. So, that means this RV is it contains R, and it's an RV is a valuation ring of K. And this is very important, this is very useful, that in some sense that through valuation If you know all the valuation rings of K, the field K, then you know how to the integral closures. Okay. 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 So there are some more properties. So I am not going into all. Probably maybe some of them I will put it in exercise assignment sheets.